Let's go one step further now. The photoelectric effect said that light strikes a metal, sometimes an electron is ejected. Well, Arthur Compton noticed in the early part of the 20th century that sometimes not only an electron was ejected, but also another photon was ejected. So you've got the original photon that strikes the metal, an electron is ejected, but also another photon was ejected. We call this the Compton effect. Now, why is this happening? First of all, what's happening? And second of all, why is it happening? A photon strikes a piece of metal, an electron is ejected, and a second photon is ejected. Now, classical theory would predict that, look, if we're going to get a photon ejected here, it's going to be the same photon as we started with. Basically, it's going to be a reflection, right? This blue photon, this high frequency photon, strikes the piece of metal, an electron goes off, the blue photon bounces off too. But that's not the case. If the photon was ejected in addition to the electron, okay, that's a big if, okay, it doesn't always happen. But if a second photon was ejected, it was observed that that photon was always less energetic than the first photon. In other words, if we start with blue light, we have to have something with a lower frequency and therefore a lower energy that's ejected. Make sense? It doesn't have to make sense why that happens right now, but just makes sense that it's a less energetic photon. If we get a photon ejected, it's always less energetic than the first one. Well, nobody could explain that one either. Let's use Einstein's photon theory again, at least in part. Okay? Light exists not just as a wave, but as a particle. So a particle of light strikes the piece of metal, another particle called an electron is ejected, another particle that's called a photon is also ejected. Compton came along and said that this is really a collision, right? Like a car strikes another car and two cars go off, right? You get the wreckage of two cars. Here we've got a collision between a photon and an electron, so that you get them scattering, right? You get this scattering of this photon and electron, just like you get the scattering of the car and the other car when they collided at the intersection. So if it's just a collision, what do we do with it? What do we do anytime we have a collision? Conservation of momentum, right? Pi is equal to Pf. So Compton said it's just a collision. It involves conservation of momentum. But people said, well, wait a second, that doesn't make any sense. How can you have a collision where we have conservation of momentum when we're talking about photons? Photons don't have any mass. There was no momentum to start, right? This is where we started with the whole deal. The photon. Something with no momentum can't produce something with no momentum and then something with momentum. It doesn't make any sense. Compton said, yeah, it makes sense if photons have momentum. Everybody else said, well, wait a second, they can't because they don't have any mass. How can you have momentum when you don't have any mass? The equation for momentum is m times v. How can you have momentum if you don't have any mass? Compton said, wait a second. Einstein said something pretty special. We haven't talked about this yet. Einstein said that energy and mass are the same thing. So although photons don't have any mass, they do have energy. And just like ice and steam are two different forms of the same thing, energy and mass are two different forms of the same thing. So they don't have any mass, but they do have energy. And because energy is the same thing as mass, photons can have momentum. That's the big takeaway from this. Photons have momentum. Despite the fact that they don't have any mass, photons have momentum. Yes. Now, the little diagram that I drew for you had blue light and red light. This isn't going to happen with blue light. Okay, the original photon has to be much more energetic than blue light, something like an X-ray, a really high energy photon. I just use blue light and red light because it's easier to draw it than it is to draw X-rays. You got to have a high energy photon. When it strikes the metal, an electron and then a second less energetic photon is ejected. And as we said, classical theory, old style physics, physics prior to the 20th century would have said that, look, hey, no problem. We didn't expect this necessarily, but we see it happening. All right, no problem. An electron's ejected, a photon is ejected. Well, the photon should be the same as the original photon, but it wasn't. So Compton resolved this by saying that photons, they have energy, just like Einstein said. But he went a step further and said, they got momentum as well. And this is really just a collision. Like when two cars collide at an intersection, here we got a photon and an electron colliding. Momentum is conserved. The photon scatters. The photon goes off at an angle. We call that Compton scattering. Now, because of that, there's going to be a change in energy of the photon, right? Because the frequency of the photon changes, its energy will also change. The scattering of the photon is called Compton scattering. The change in energy is called the Compton effect. Don't get hung up too much over these terms, okay? If you remember that this is Compton, you're probably okay. I don't think you're going to see a multiple choice question where you have to distinguish between Compton scattering and the Compton effect. So let's deal with finding the momentum of a photon now. Remember that we said probably on the first day of this year, of this semester, we said that momentum is equal to mass times velocity. Okay? Compton said that photons have momentum. We said, how do photons have momentum when they don't have any mass? Einstein said that energy and mass are two different forms of the same thing. Probably the most famous physics equation ever, one of the least understood physics equations ever, you're about to see for the first time this year. What is it? A couple people in the back have been waiting for this one for a while, it looks like. E is equal to mc squared. What this means is that energy, this is the energy equivalent of this mass. This is the mass equivalent of this energy. It's like saying this much steam is equivalent to this much ice. It's the same thing, just two different forms of the same thing. Now, we're not quite, the analogy isn't quite true because, of course, we're not talking about different states of matter here like ice and steam, but it's an okay analogy, right? Two different forms of the same thing, energy and mass, ice and steam. You have a certain amount of mass, hey, what's it worth in energy? You have a certain amount of energy, what's it worth in mass? Okay, we want to find the mass equivalence of a certain amount of energy. We know that photons have a certain amount of energy. That's easy, we can find that. H times F or hc over lambda. Let's find out how much mass it's worth. Once we do, let's plug that into here. So instead of m times v, it becomes E over c squared times v. Now, v is what? Speed of light. So let's call it a c. One of the c's cancel here. And we end up getting P is equal to E over C. Now on your data sheet, that's actually written this way. E is equal to P times C. So in your data sheet, you can see the momentum of a photon, but it's actually expressed in terms of its energy. Energy is equal to the momentum of the photon times the speed of light. Now, we can also replace E with H times F. That also appears on your data sheet. We can also replace E with hc over lambda. Well, that's a little awkward, that equation. Cancel out the c's. That also appears on your data sheet. So in the top right-hand corner of your data sheet, you're going to see these three new equations. They're all for the momentum of a photon. the momentum of something without mass. Now, if you get a question that asks you for the momentum of a proton, what are you going to use? M times V, because it has mass. It's just like a car, right? But if you're talking about a photon of light, then you're going to use one of these three equations. Does that make sense? Okay. Have a good night, guys.